Our presenter for this session is Dr. Kristine Nichols from Kutztown, Pennsylvania. Dr. Nichols is a world-renowned leader in the movement to regenerate soils for healthy food. Healthy people and a healthy planet. Dr. Nichols was the chief scientist at Rodale Institute from July 2014 to July 2018, where she oversaw approximately 15 research trials. Prior to joining the Institute, Dr. Nichols was a research soil microbiologist with the USDA, Agriculture Research Services in the North Dakota for 11 years, and a biological laboratory technician with ARS in Beltsville, Maryland for 3 years. Her research and professional achievements have focused on the impacts of cropping and grazing systems on soil microbiology, nutrient recycling, and social aggregation to improve soil health and water quality. Her most recent work involves mycorrhizal fungi and the investigation of glomalin, the substance produced by AM fungi. The title of Chris's presentation is Building Resilience Through Soil Health to Announce Human Health. Please welcome Chris.
Thank you, everybody. I'm a little bit of a wanderer, so I'm just going to kind of wander on the stage, hopefully not fall off. And I want to thank you all for being here. I'm very happy to be back here in Kansas. I was here last year for this conference, and it had been a while since I had been in Kansas, and it was really exciting for me to be able to see everything that's going on back in the Great Plains. After I moved to the East Coast, it was very exciting to see how things are progressing at a rate in which we need them to progress in order to be able to build up these resilient systems that are going to thrive, but are also going to be able to concentrate on not just the health of the soils, but also the health of the food that we're producing. So I wanted to begin by talking a little bit about soil health. And this idea, this is the accepted definition of soil health. But as I was looking at this definition of soil health, it really was something in which we're not focused on the soil. We're focused on what we can take from the soil. This is about us. And if we're really going to get the system to work, we need to be focused on the soil and the soil foundation, what the soil is able to give us. And in doing that, we need to recognize that we are actually in a chess game with nature. We've always been in a chess game with nature. But what we want to do in this chess game is we no longer want to be losing the game. We're never going to win the game. The point is not to win the game. The point is to keep pieces on the board. The point is to keep the system working. As we focus on just chemical and mechanical tools to address our issues, what ends up happening is nature takes our pieces off and will end up putting us into checkmate. And then what we do is we come up with a new chemical or mechanical tool, and we just wipe the board clean and we restart. But every time we restart, it's like losing a layer of soil. And we can't afford to continue to do that. We can't afford to continue to restart the game. We don't have that much soil left in order to be able to do that. So what we want to do is we want to insert a biological approach first. It doesn't mean you can't use mechanical or chemical tools. It means that you need to think about what biological solutions you could utilize to address the issues that you're seeing before you go ahead and utilize a chemical or mechanical tool. So what we're trying to do is actually focus on building these resilient systems that are going to resist various types of issues that they're confronted with, that are going to improve the nutritive quality of what we're growing, and are going to improve overall productivity. And I say overall productivity, and you notice I don't have the Y word here. If there is one word that I could eliminate from agribusiness, it would be the Y word. The Y word is yield. The bank doesn't take yellow grain. The bank doesn't care. The bank takes checks. And the biggest thing that influences your bank account is how much you withdraw from that bank account. When you focus on biological tools to address your needs, it's looking at who's writing the check and how big of a check you're writing. Overall profitability is about reducing the number of checks that you write and how big those checks are. What you want to focus on is having nature, having the plant write the check. Because the plant is going to be feeding the soil. I mentioned the fact that we have various types of issues, and I said issues a few times. Issues are what we continue to look at and continue to try and address. We continue to say that there are issues out there. It's too hot, it's too cold, it's too wet, it's too dry, I don't have enough fertility, my soil's too sandy, my soil's too heavy. I can't do this. Those are issues. We don't focus on the problem. And one of the things that I think is because we've never fully identified what the problem is. As I worked with this microbiology in the soils, what I found that I think the problem is the root of the problem is the root of the solution. It is being able to have more carbon in our soils, being able to have more living roots in our soils. We need to re-carbonize our soils. If we do that and address that problem, we're going to be able to resolve the issues that you see. That's what building resilience is about. That's what creating resistance is about, is recarbonizing our soils so that we will have the ability to address those issues. We will have a wide diversity of organisms in the soil that will be able to thrive and confront whatever type of issue is being placed in front of them. So we need to focus in this picture, we need to focus not on the soil food web, as much as focusing on where that food web starts. That first trophic level. As you can see, without having a plant there in the system, without having photosynthesis occurring, there's no food web. It doesn't matter if you have a nematode or a fungus or a protozoa or a bird or even us. If we don't have plants growing in the system and we're not recarbonizing our soils, our system is going to collapse. There is no web there. There is no complex diagram. So it's really important for us, again, to focus on that problem and focus on what we can do to address this. And what we can do, first off, to address this, if your problem is I don't have enough carbon in the soil, how do I put carbon into the soil? We need to capture and optimize the best system ever created for solar energy collection. Because what that system does is that system takes the energy of the sun and it holds that energy in the bonds between carbon atoms and other atoms. But it's collecting that energy, and then the carbon that's there isn't just where the energy is. The carbon forms the building blocks for every cell, every molecule, every enzyme, every protein, and almost all life on planet Earth. You, me, everybody. This is important for us to recognize, because think about how many cells are just in your body. How much carbon does it take to energize and create those cells? If we don't have carbon in the system, we're not going to get things to work. And the plant is only doing photosynthesis when the plant is living and growing. So how much living and growing time do you need in the system? How much do you need to be able to get the carbon and the energy that's required to get this to function and work? So what we really need is a brown revolution. We need to focus on what I'm going to refer to as eco-functional intensification, which means that in every square foot of your farm, of your farmscape, you're going to be looking at how best to utilize that and how much plant growth I can have on that area. Here in Kansas, in this area of the country, we need to have things growing a minimum of 300 days out of the year. Up in Canada, where Blake's at, he gets 280. He gets 20 days off, 20 extra days. You're welcome. We need to have these systems in which the sun shines 365 days. Why are we not optimizing that? We utilize things like temperature and precipitation patterns as an excuse. What we need to be focusing on is optimizing our landscape use, maximizing the efficiencies of the system, not doing more work but less, creating multiple enterprise systems to help us with profitability, recognizing that everything costs, and in this cost, we're looking at the cost of carbon and energy. That's the checks you want to write. That's the checks you want to get the system to write. And when you do this and you focus on all of these other plants that you could put into the system, it's going to redistribute your risks, again, help you with multiple enterprise systems, and it's going to improve the nutritive quality of what it is that you're growing. So we need to look at how we may be able to apply the principles of soil health in a little bit of a different way. So I laid them out in this pyramid design. And I put them in this pyramid design because I think that, one, sort of thinking about the structure of this isn't a hierarchy. Because the structure of a pyramid, the reason the pyramids have been around for thousands of years is how their structure actually helps to keep every layer in that pyramid intact. The pressure of the upper layers helping to put pressure on the bottom layers so that that downward pressure keeps those bottom layers intact. The bottom layers creating a foundation to be able to hold up the upper layers. Again, this isn't about a hierarchy. It's about looking at the design and thinking about the design and how they're all integrated together. And if you want to think about how to apply this to your system, what I want you to do is essentially think about treating the soil like you want to treat yourself, like you're supposed to treat yourself. Like you're supposed to treat yourself in order for the system to perform essentially like gold medal winning Olympic athletes. You want your system to be the best, right? You want everything to be functioning at peak efficiencies. You want it to perform. What we've allowed our systems to do is become lazy. What we want to do, what we need to do is not allow our systems to be like the typical American. I am the typical American. I am obese, malnourished, and I don't exercise enough. I am not a gold medal winning Olympic athlete. I represent that very well. What we want is we want our systems to perform better. So the first thing that we need to do is make sure that our systems get fed. The first thing an athlete needs to do is to look at how they're feeding themselves. Making sure that you have small meals, be a grazer, consistent eating. What this means in our system is that foundation to our pyramid. Because the food flowing through the system is the carbon that comes from photosynthesis. The more you can have living roots, something green and growing, the more functional this system is going to be. And again, we need to focus not on the number of growing degree days you have, but on the greenness index. How much green can we get? How often can we do that? And if you look at maps, go on the internet and look at maps of greenness indexes. If you look at that in your own region, you'll see how much greenness, how much photosynthesis goes on in your ecosystem. Not where you're growing crops, but in the system where nature has been allowed to grow plants. Because nature will not allow there not to be green if there's any other option. I lived in North Dakota for 11 years. I was born and raised in Minnesota, near South Dakota, not too far from where Rick's at. And what it is that when you look at that, I've been out taking soil samples and out in those fields and out in my father's pastures in the middle of winter. And if there's not snow on the ground, there can be something green. Because we need, again, nature needs to have the optimum level of photosynthesis. Why don't we apply this to our crop systems? We're going to lose the chess game if we don't. We need to follow those ideas, and we need to focus on vegetative growth. Vegetative growth is when the plant is going to be harvesting sunlight. It's going to be capturing that energy. And again, it's not focusing on temperature, it's focusing on how many days of sunlight do you have. Now in Canada, the sun doesn't go down and not come up. In most of Canada, if you go far enough north, there are a few days like that. But in most of Canada, the sun is up 365 days. Again, why aren't we doing that? I repeated that because it's important for us to think about this. We focus on temperature because we have a tendency to humanize things. We have a tendency to think of things in the same way that a system, that our bodies work. So we go outside today and it's cold. I don't want to have a plant out there because it's cold. Plants don't feel cold. They don't have a nervous system. They don't sense temperature in the same way that we do. Yes, there are plants that are adapted to growing in certain environments better than others. The prime example that I love to pull out is corn. We're trying to grow corn everywhere. Corn originated as a perennial tropical grass. Tropical. Why do you want to grow corn in Canada? It's a tropical grass. These are things that we need to think about. Yes, plants are adapted to certain environments, but that doesn't mean you can't grow something there. It means that you have to think about what plants might be able to optimize harvesting sunlight on November 15th, on December 15th. I'll give you January off, because I'm nice. But other than that, you need to optimize this system. We need to think about plant selection. And this means sometimes going and looking at old plants, not just new plants, but old plants. Go look at old extension center records. Go look at old information and see what plants were growing previously. In the 1950s, in the 1940s, in the 1930s. What was happening in that system? How do you optimize this? Doing relay cropping, double cropping, polycropping, put annuals and perennials and perennials and annuals. Intensify the system. I said eco-functional intensification. This is not about having less, this is about having more. This is about pushing the system, energizing the system. Because we're functioning again on a carbon economy. That's who's writing the checks, is the carbon, not you. If you want to be profitable, you want the plants writing the checks. And when we do that, we're going to work with the community, the diverse array of macroscopic and microscopic organisms that exists in our soil. There are millions of different species of organisms, billions of them, potentially trillions of them in every handful of soil. If we re-carbonize that environment, I mean, think about that. Not just the cells in your body, but in healthy soil, we want to have billions to trillions of organisms in every handful of soil. How much carbon does it take to keep that life going. Even when they're single-celled, if there are trillions of single cells, what does that mean? How do we get that functioning? We need to look at basically maintaining a system in which the organisms are essentially starving and homeless. That's your job. You need to feed them and you need to keep their house intact. Every day you need to wake up and you need to tell yourself, what am I doing to feed somebody? Or am I taking their food away? And am I keeping their house intact and allowing them to build it? Because they will build it. You don't have to build the house. You don't have to put any energy into building the house. You don't have to do any of that. They will do it themselves. But how do I keep them in a house and keep them fed? That's all you have to do. And yes, there may be days, January, when you're not feeding them. It's just the way it works. And that's okay. But you have to recognize that you have to make up for that. You have to intensify the system to make up for the days that you're not applying the principles to feed them or keep their houses intact. Because again, we have this interactive carbon economy, and where this economy goes is you have plants that will trade carbon to fungi and bacteria and other organisms in the soil. Things like mycorrhizal fungi and rhizobium bacteria, nitrogen fixation that occurs, not just with rhizobium, but also with free-living nitrogen fixers. You have bacteria that solubilize and release phosphorus and make it available. Again, you have organisms that help to create aggregates, the pellets in the soil. That's their houses. That's what they engineer. And when they make those aggregates, between the space of those aggregates is the open space, the porosity. That open space that allows the water to come into the soil very, very quickly and the water to be held in the soil for a longer period of time. You build up the structure of the soil so that it physically can help to support the plant and hold the plant up, so that the roots have a good anchoring spot for them to survive. You want to have this diverse array of this carbon economy that's going to be functioning and flowing through this system. These are soil aggregates. This is what the aggregates look like. And again, the organisms will build that structure. They will create that environment. And when they do that, they also go through and produce biomolecules that help to stabilize those aggregates. Glomalin that was discussed in my introduction. Glomalin is something that will help to stabilize those aggregates. So when you engineer and you build a house and you have the wooden frame of the house, if you don't put some sort of weather sealant on the outside of the house, when it rains, or there's wind, or there's some other type of exposure to the house, the wooden structure blows the house down. Remember the 3 little pigs? The brick house was the one that stood. Brick houses have that sealant, that structure on the outside that creates the rigidity that helps to hold them up and support them, allows them to withstand the conditions. That is engineered by the microorganisms. It's created by the microorganisms when they have enough carbon resources to do it. So if you look at this, this is a measurement of aggregate stability on the bottom. Basically, I took those aggregates that are on the top, I collected them out of the soil by passing the soil through a series of screens, and then I just added water to those same dishes on the bottom. When you add water, and you add water to aggregates that were designed and built in a conventional till, that's CT, spring wheat fallow system, there's not enough carbon influx on an annual basis, and there's too much physical disturbance by tillage, so those aggregates fall apart. Because the tillage is requiring the fungus that helps to engineer and create the wooden frame structure, and helps to create the glomalin. That tillage basically requires the fungus to have to go through and rebuild the fungal network, the hyphal, the structure, its body, every time there's tillage. So it has to go into a rebuilding phase and use carbon resources for that. So it doesn't have the carbon resources to make the glomalin to put the bricks on the outside of the house. So the next one is a no-till spring wheat, winter wheat sunflower system. Spring wheat, winter wheat. Sunflowers, it's a little bit better, but how much carbon time are they optimizing? Vegetative growth is when we're optimizing carbon. The vegetative growth of wheat is roughly about 4 or 5 weeks. That's it. Out of 52 weeks, you gave carbon to the soil for 4 to 5 weeks. Is that really going to work? So in that system, even though you weren't doing tillage and it didn't have to rebuild the hyphal network, because we weren't optimizing sunlight time, sunflower did a little bit better than wheat did. We weren't optimizing sunlight time. So again, we didn't get enough glomalin formation. We didn't get enough bricks on the house. So the houses fell apart. The last one is a moderately grazed pasture. Nature is optimizing photosynthesis time. We're not doing a lot of heavy disturbance, although we have the cattle that are out there that are doing some soil disturbance. So some of the hyphal networks get broken up by cattle, which is fine. A little bit of rebuilding and in reinforcing and enhancing the hyphal network is okay. You just don't want to have that happen at a large scale on a repeated basis. And we get 93% of those houses that got built with bricks on them and are going to stay together. This is what we want to do with the system, and when we do that, this is a picture of Gabe Brown's ranch. Many of you have probably heard Gabe Brown, some of you have probably seen this picture, but when we do that, this is what we can get. This is how we can optimize the system. Because the porosity that's created between those aggregates now allowed for Gabe to take his infiltration rate up from 1/2 inch per hour to 8 inches an hour. And now it's even more than that. But this was 8 inches is about the time that this rain event happened. In North Dakota, where Gabe's at, the average precipitation is somewhere between 12 to 16 inches. What we're finding is that as you do this, that aggregation that is created, the pore space, is like putting curves in a road. The shortest distance between two places is a straight line. The more curves that you have, the more tar it takes to make the road. If you think of the tar as the same amount of water that you could put into a space, so the more curves and bends that you have on the road, the more water you can get into the soil. So when we had this rainfall event of 13.6 inches of precipitation in a 24-hour period, this was from the next day. There's no standing water. I was flying into Wichita yesterday, and I saw standing water in the crop fields. There should never be standing water in your field. If there is, that area of your field should not be in crop production. It should be a wetland area. In North Dakota, in the prairie pothole region, we took potholes and we made them into crop production. No wonder we get standing water there. Again, it's about eco-functional intensification. You can still utilize that landscape, even putting it back into a wetland. It becomes landscape that you could use for a different enterprise system, or landscape that you could use to reduce the checks that you're writing. Because it's now going to be a diverse environment where you're going to have pollinators and you're going to have other animals and you're going to have greater level of plant diversity, all of these things that are going to help to manage issues that you see in your system. How is it that we can utilize the system better? When you create that pore space, that open space that goes around the curves, instead of creating large open space that sometimes we like to do with mechanical tools, so I need porosity, so I'll go out there and I'll just poke holes. Or I'll use a tillage tool and I'll just open it up and I'll have these big cracks, and that will allow for the water to get in much more quickly. Yeah, the water's going to get in fast, but the thing is that water is not going to stay there. Because sun is constantly pulling water off of the surface and gravity is constantly pulling water down. If we want our water to be there, this 13.6-inch rainfall event was pretty much the rain for that season. We need to build resilient systems that are going to get 13.6 inches of rainfall in. Again, that's the precipitation you have for that environment. That's your average precipitation. If you get it in one event, you got to get it in and you got to hold it. The curves keep it there. It's essentially like having kinks in a straw. If you get a straw and it's got a bend in it, and you put it in and then you try and take a drink, and then, nothing comes, and then you go, nothing comes, and then you throw the straw away. That's what we want sunlight evaporation and gravity to have to do. If there are bends and kinks, we're going to hold on to the water. We're going to keep that retained in our system. So we want to make sure that we're going to have water in our system, and the other thing we want to do for managing water in our system is managing fertility. Managing how we get nutrients into that system. Because the nutrients have to move in a water film. They have to be solubilized. They have to be in water. The more that the nutrients are separated from the rhizosphere and the microorganisms aren't allowed to be able to get those nutrients to the plant, the more water it takes to move them to the roots. We don't know, as scientists, how much water it takes any plant to grow. And any scientist who will tell you that is a fool. We have no idea. Because the water that we talk about is the water that is a part of the entire ecosystem. And if you don't have healthy soils, you're going to use a whole lot more water than you would use in soils that are healthy. That's not the water the plant needs to grow. That's not the water that's cellular. That's not the water that's in the plant cells. That's part of the water that helps the system function. That's what we've measured. If we redesign our systems and we innovate our systems, how much more efficient can we be? How much can we capture? Dryland desert systems, nature doesn't have them not have plants growing on them. Why do we think that we can't do that? I was in the high plains of Colorado, and they were telling me that this was a desert system. And I was like, seriously? We're driving around and stuff is green and growing. Not in the crop fields, but in other places. When we have that, that is something that is functioning as nature wants it to function, at that higher level. It's optimizing the system. So the other way that we can address this, again, is not just keeping something growing, but if you want to be healthy, you have to eat a diverse diet. Mother was right. You got to eat the Brussels sprouts. May not like them, but that's what has to happen. We have to have a diverse diet in our ecosystem. That diversity has to exist not just for the plants, but also for the micro and macro communities of organisms. We need to look at having plants that have different carbon to nitrogen ratios. We need to look at how we're going to manage the system, and when we have diversity in the system, it's going to help us manage weed issues. Because weeds are nature's way of telling you that a plant should be there. Why don't you choose the plant? If nature says a plant needs to be there, you got to put a plant there. Your choices are to let nature choose the plant, which may not be optimum for your system and may not make you happy, or you could choose the plant. You're playing a game, a chess game, in which you're not going to win. But keep those pieces on the board. If nature says, you got to do this, you better do it, or nature will take your piece, and you're going to be in checkmate. You need to figure out how this is going to happen. Because as we get the greater level of diversity in our plant communities, we're going to get a greater level of diversity in the macro and microbial communities, which is going to help with nutrient cycling. It's going to help to build the resilience in the system. It's going to help to optimize everything that you have for managing pests and disease better. Again, creating competition. The best way to manage a pest issue is to outcompete it, not to spray it with a chemical. Because what those organisms do, the minute that they get sprayed, is yes, you may be killing some of them, but they're always going through creating genetic diversity. Super weeds is not a new thing. Super weeds have always existed. They were plants that in the genetic diversity knew how to overcome a particular chemical. What we did is we killed all of their competitors, and so they were the ones that produced seed. So now we said they're super. They're not super, they're just normal. They're doing what they're programmed to do. Nature is always going to look to try and take your piece. Keep your piece on the board. Don't let it be lost. Exercising our system. This is one too that I don't think that we think about at all. And it's our nature. And it's okay. Our nature is to, when we see an issue, when we see a plant that's struggling, when we see an animal that's struggling, you want to take care of it. But what we do is we prophylactically, before there's even a struggle going on, we're going to wrap our crops or our animals in a bubble. Anybody ever see The Boy in the Bubble movie? Boy in the Bubble? The boy in the bubble wasn't expected to live very long. He didn't really have much of a happy life. And part of the reason was because he wasn't exposed to the stressors. We need to have strong, resilient plants. We need them to thrive no matter what it is they're confronted with. And to do that, we need them to exercise. Again, to have gold medal winning Olympic, the best soils that you possibly can, you need to exercise. We need to make sure that that exercise, we look at the frequency of the exercise, the frequency of the stresses, not too much stress. Again, if you're a good athlete, you understand that you can't put your body under too much pressure. Not too much stress. Not, again, the frequency, the intensity, the scale, and the timing. Think about how those stressors are occurring and when they're occurring, and how we can optimize that type of a system. So what does this mean? Oftentimes, the stressors are, again, tied to the carbon economy. They're tied to the fact that the plants need food. That is a stress on the plant, or that the organisms in the soil, the organisms need food. That is a stress on the plant, because the plant has to give up some of its resources in order to feed the organisms. What ends up happening is when you reduce the inputs, you keep the job of the organisms. You keep them functioning. If they don't have a job, if you outsource their job, if they don't provide some value to the plant in the carbon economy, they don't get fed. If they don't get fed, they can't grow. Don't have the diversity in our system. So what we've done is we've created these systems that are very resource intensive instead. I'm going to supplement the jobs. Well, supplementing became outsourcing. And outsourcing became elimination. Because we took the place of the organisms, utilizing various types of fertilizers, utilizing various types of pesticides, and utilizing irrigation. Everything that's part of a resource intensive that checks you have to write is a part of outsourcing the jobs of the organisms that you need to have in healthy soil. If you check you right, steals a job. How do you want to create your system to keep the jobs in place? One of the dirty little secrets of agriculture has been this idea of nutrient use efficiency. We have always known that the use efficiency of synthetic fertilizers is bad. 50% or less. It's always been that way. When recommendations are made for fertilizers, they're adjusted for that. You pay for products that are 50% or less effective. Why do you do that? If I bought a car and it only got me 50% of the way to work, I would go back to the car dealer and I'd be, show me the money. Because you owe me something. How do we get our systems to be more effective? And one of the things these graphs teach us is the top graph is our increase in global cereal yield. So these were done on a global scale. This was a global study that was done looking at everything. And we've seen since 1960 an increase in yield, which is logical and it's good. The bottom graph is what's called a nitrogen use efficiency curve. Essentially what that bottom graph shows us is this is on this graph it's a megaton of cereal, but basically on a per bushel basis, the amount of nitrogen fertilizer that it takes. What this graph shows us is essentially that it takes more nitrogen today because that efficiency has gone down. So our yield per the amount of nitrogen fertilizer added has gone down. It takes more nitrogen today to produce a bushel of grain than it took in 1960. This is more nitrogen that we add to the system. And think about it, in 1960, how much synthetic fertilizer was added to our fields? Yes, yield has increased, but it hasn't increased proportionally to the amount of nitrogen fertilizer, to the amount of fertilizer that we're adding. And the reason is that in 1960, more than 50% of the nutrients came from the soil, came from the activity of the organisms. As we outsource their jobs and their activities, guess what happens? That 50% is no longer available. So it requires us to put more inputs into the system. We can get nutrients from the activities of the organisms that are in soil. Mycorrhizal fungi can provide for up to 90% of the nitrogen and phosphorus needs of a growing plant. They do that by working with other organisms, such as phosphate-solubilizing bacteria and nitrogen-fixing bacteria. They do that by working together in these complex communities. And what they'll also do is they'll also help to transfer water, not just nutrients, but water. They also can help to increase the induction or the creation of various types of antioxidants. When you improve nutrient use efficiency, when you improve the availability of various types of nutrients, micronutrients to the plants, what ends up happening is the plants can utilize those resources to create the biomolecules that the plant needs, antioxidants and polyphenolics, the biomolecules the plant needs to be healthier, but it's also important to our own human health. Because what are we missing from our diets these days? It's not the minerals entirely. We're missing antioxidants and polyphenolics, those complex biomolecules that aren't in our food anymore. And they come directly or indirectly. Some of them are made specifically by microorganisms. Some of them are made from the resources that microorganisms provide. And some of them are made by the microorganisms stimulating that creation. All of those things can happen in these diverse communities. And again, it's really important for us to look at this because this is how we're going to get this system to function in order to be able to reduce the checks that you write. Wouldn't you want to produce food that has everything in it that a human being needs to have from that particular food, higher nutritive value, which hopefully someday you can market on, as opposed to marketing on the Y word. Market things based on their value, their intrinsic value, and then at the same time, write fewer checks to produce them. And one of the ways in which we can do this is by looking at this plant-to-plant nutrient transfer that occurs. So we're going to talk about 5 organisms, 2 plants, 2 bacteria, and 1 fungus. Mycorrhizal fungi, phosphate-solubilizing bacteria, nitrogen-fixing bacteria. We're going to have a grass, a non-legume plant, and we're going to have a legume plant in this system. The fungal hyphae is going to connect the roots of the legume plant and the non-legume plant together. The non-legume plant tells the fungus, it says, I need phosphorus and nitrogen today. You go out there and get that for me. The mycorrhizal fungus says, okay, I'll go out there and get that. I have phosphate-solubilizing bacteria that colonize my hyphae, and it just so happens that I'm growing into the roots of this legume plant that seems to have excess nitrogen. So I will take those things and I will bring them to you. So the mycorrhizal fungus takes some of the carbon from the non-legume plant and it gives some of that carbon to the phosphate-solubilizing bacteria. The phosphate-solubilizing bacteria produces enzymes. Those enzymes are able to release phosphate that's normally not available. They'll release that phosphate. That phosphate is released because those phosphate-solubilizing bacteria live on their fungal hyphae. That phosphate is released right outside the door. So the fungus just has to open up the door. When the fungus opens up the door, the phosphate comes flowing in. Now the fungus also goes over to the legume plant and it takes some of the nitrogen that's in the roots of the legume plant. The legume plant then says, you know what? I need something too if you're going to do that. So you can take the nitrogen from me, but I need to have some phosphorus. So the mycorrhizal fungus says, cool, I got this phosphate-solubilizing bacteria that's on my hyphae that all I have to do is open up the door and the phosphate comes flowing in. So I can handle what you need and I can handle what the non-legume plant needs. Now, the legume plant then goes to the bacteria that's in its roots, the rhizobium bacteria, and it says to the rhizobium bacteria, you got to kick up this nitrogen fixation because in order to do this nitrogen fixation that I need, I also need to give some nitrogen to the mycorrhizal fungus. The mycorrhizal fungus can give some of that nitrogen to the non-legume plant. So now the rhizobium bacteria says, all right, I can do that, but what you have to do is you have to give me more phosphorus because in order for me to fix nitrogen, it's a very energy-intensive process. This energy-intensive process basically is the Krebs cycle. It requires essentially a molecule called ATP, adenosine triphosphate, where there are 3 phosphate groups that are bound to an adenosine molecule. Now essentially what happens is in this cycle, one of the phosphate groups gets ripped off and it becomes ADP instead of ATP, adenosine diphosphate instead of adenosine triphosphate, but you can't take the phosphate group that got ripped off and put that back on and make it ATP again. Now when that phosphate group gets ripped off, electrons are released. Electrons, as they pass through a membrane, essentially fire the cell. And that allows for nitrogen fixation to occur. It requires essentially about 32 ATP cycles in order to be able to fix one molecule of nitrogen gas, dinitrogen. So it's a very energy intensive process. We know it's very energy intensive because when we're using nitrogen fertilizer, if energy prices go up, fertilizer prices go up. So it's again a very energy intensive process. So the legume plant says to the mycorrhizal fungus, you got to get me more phosphorus because I got to give some phosphorus to my rhizobium bacteria in order to do the nitrogen fixation. So the mycorrhizal fungus says, all right, you give me a little bit more carbon, I'll give that to the phosphate solubilizing bacteria. The phosphate solubilizing bacteria will solubilize more phosphate, and then I'll be able to open up the doors and all the phosphate will come flowing in. So the mycorrhizal fungus does this, they open up the doors, phosphate comes flowing in, and all of a sudden, with phosphate flowing and nitrogen flowing and moving through different plants in the mycorrhizal fungus, a traffic jam occurs. We all know what traffic jams are like. The traffic jam essentially means that it can't satisfy those needs. So the mycorrhizal fungus goes to the non-legume plant and it says, you know what, I'm sorry. I just can't get everything that you need at the level that you need it. And the non-legume plant says, you know what, I have this secret code to phosphate solubilization. I'll tell you how to solubilize enough phosphate to get more phosphate into your fungal hyphae and hold that against a gradient. Because normally you can't put that much phosphate in your hyphae, but I can tell you how to do that. So the mycorrhizal fungus then takes the secret code in order to be able to hold more phosphate in the fungal hyphae. It will utilize that secret code to get that enough phosphate to be able to give the phosphate to the legume plant, so the legume plant can give some of that phosphate to the rhizobium bacteria. The rhizobium bacteria can do nitrogen fixation. The nitrogen fixation will allow enough nitrogen to be made so that there's enough nitrogen for the legume plant as well as nitrogen to go into the mycorrhizal fungus. So the mycorrhizal fungus can take some of that nitrogen to the non-legume plant. It also is going to pick up phosphate along the way that came from the phosphate solubilizing bacteria, and it will give that phosphate then to the non-legume plant. Everybody's needs are satisfied instantaneously. Why don't we tap into this? The best that we can do. Thank you. The best that we could do to mimic this is to have all of the farm kids out there, all of the FFA kids out there walking up and down the fields 24/7, no longer going to school, sorry young man. No playing games, no movies, no nothing. You get to walk up and down the field with little syringes and inject those into the roots. That's the best that we could do to mimic this system. We can't do it better than nature can do it. And the other thing that happens with this is this happens when the plants need it to happen. Not on our time, but on their time. That optimizes the efficiency of that relationship. So, just got a few more things that I want to go over. We want to stimulate as well the insect community, the arthropods, not just the microscopic, but also the macroscopic community. That's going to be a big part of what's going to be happening in the system. Because the insects are really important, not just in helping to act as pollinators, not just helping to manage predator and prey relationships and pest and disease types of relationships. But one of the things that we found is, again, a little bit of insect wounding actually helps to stimulate the formation of these complex biomolecules, because again, it's a stressor on the plant, stimulate the formation of antioxidants and polyphenolics that the plant needs to be healthier and that we need to get from our food. We can't wrap our plants in a bubble. We have to have these things occurring in this system. We also want to manage livestock in our system. And livestock of all sizes. This again is about the insects that are in the system, not just about the animals that are going to be grazing. And how we want to do this is, in some cases, watching the way the animal grazes. Now hopefully this will run. There we go. So if you watch this cow, what the cow does is the cow will actually use its tongue. It wraps its tongue around the forage. Doesn't use its teeth. When it wraps its tongue around the forage and shakes its head, that's going to pull and tug at the plant. That pulling and tugging at the plant will essentially break off root hairs below ground, which releases a lot of carbon into the soil and into the system. It also is really important when that happens because the wound pattern is basically like ripping at the leaves. And when you rip at the leaves as opposed to biting at the leaves, which is what we're going to see next. Now, I apologize because for some reason this video wants to go upside down. And the tech guy was looking at it too, and we couldn't figure out why this video wanted to go upside down. So everybody go like this and look at the sheep. No. So if you look at the sheep grazing, oh, and this is going to be off the slide too. Sorry. The sheep, if you watch sheep grazing, it's their teeth that are making that wound. And it's a single wound that will be occurring. That single wound, as opposed to this shredding of the leaf, stimulates different carbon allocation. So when you hay or slice, you can't get the same level of carbon allocation as you get when you shred the leaf. Which doesn't mean that you need to have cattle instead of sheep. It means that you manage them differently. If you're managing livestock and you're putting that into the system, you need to have it designed so that it does something different. So what we want to do is essentially take care of our systems. So the other thing that we're going to look at is protecting the soil surface. And I know I'm over time, but I'm going to go one more second. We want to protect our soil surface. We want to put soil armor on there. Crop residue, living plants, mulches, compost. All of these things are protecting the surface of the soil. It's estimated that the intensity of raindrops hitting the surface of the soil on a per acre basis is equivalent to 20 tons of TNT. Explosive forces are hitting your soil and destroying that soil structure, those soil aggregates, breaking up that habitat. Your job is to put armor on that soil to protect it. And then we want to reduce the disturbance to our soils. Again, all of this part of that pyramid design that's going to be able to grow the health of the soil. Every layer is important. Every layer adds downward force and foundational forces to maximize the efficiency of the system. So with that, we now have put together our pyramid. You know the steps to go out there and create a healthy soil. Go out there and do your job. Don't be like a senator or a representative that we currently have. Do your job. It will make you money. And that's the bottom line. Thank you.